So here we define what is tangent space. So the tangent space at a point that is a x star on the surface, x star on the surface, and that surface is defined by x. This equals to x, which is element of Rn, such that this Hix that equals to 0. Okay, so this is your surface, which is the feasible region, which is comes from the equality constants. Okay, so this is the set, and that set is denoted by T of x star. This equals to, the definition of this equals to collection of all y such that derivative of this h x star y, this equals to 0. Okay, so this is a definition of tangent space. Okay, and here note that the tangent space that is t of x star, this is basically the null space. This is the null space of the matrix of the matrix that is dx star. Okay, so the tangent space is the subspace of Rn. Space of Rn. Okay, so if we take example and try to find the tangent space, so if we assume that let any surface S, that is if we take simple problem, so that's why we take R3, okay, and we take some equality constants. So suppose our H1x that equals to 0, and our S2x this equals to, suppose, x1 minus x2, this equals to 0. So you have two equality constants. Okay, so then your problem is then find the tangent space of S, then find um, tangent space, okay, at of S. Okay, so of S. Okay, so now the solution is this problem is we have to find the derivative, because here you have to find this derivative of x star. Okay. So here x star means your x point in other regular point. That's why we take here x star. Okay. So we have the derivative of hx. So this is a simple derivative of hx means this is the gradient of h1x, and this is gradient of s2x. So this is the total derivative, that is gradient of h1 and gradient of s2. Okay, so this equals to, what is the gradient of h1? So h1 is 0, so that's why if we h1 is okay, h1 is some function of x learning. Okay, suppose h1 x is equals to x1, and that equals to 0. Okay, suppose this is x1. Okay, so here, if you differentiate with respect to x1, this is 1, x2 0, x3 0. This is first term. And if s2, if we take x1, this is 1, x2 minus 1, and 0. Okay, This is the derivative of that thing. Okay, and because this gradient of h1x, this equals to 1 0 0 transpose. Okay, because this is a vector, and similarly gradient of h2x, this equals to 1 minus 1 and 0 transpose. Okay, so here you look here, this gradient of h1, gradient of h2 are linearly independent. Okay, so here we right, because your gradient of h1x and gradient of h2x, these are linearly independent. These are linearly independent when we evaluated at any point of S. Okay, so at any x that belongs to that surface. Okay, and all the points of this surface are basically regular. Okay, so these are regular. Okay, so now you have to find the tangent space. So now the tangent space, the tangent space of at any point, at any arbitrary point of S, is basically defined by this Tx. Okay, the tangent of this space, and this equals to the collection of all y's such that gradient of this derivative of that. Okay, the derivative of this, so we can write this is explicit form, so we can write this gradient of h1x, okay, transpose y equals to 0, and gradient of h2x transpose y equals to 0, or you can write this in this manner, or you can write collection of all y's such that derivative of that hx, okay, of y that equals to 0. Okay, derivative of that, this means gradient of that into y. So this multiplied by y, this multiplied by y. That's why we take this in two separate. Okay, either write in this notation or you can write in this form as well as. Okay, so now if write in this form, so this equals to y such that if we write derivative means what is the value of derivative? That value is this thing. So here the derivative of that is 1 0 0. Here 1 minus 1 0. This derivative of that into y. Y be the element of this dimension is same. This tangent space, there is a space of Rn, same dimension. So that's why here y has dimension as 3, because this x has dimension has 3. Okay, so y has also dimension of 3. So that's why here you y1, y2, and y3. Okay, this product that equals to 0, and you are try to find what are the value of this vector y. Okay, so here if we multiply here, so you get here, this means first equation you get y1 plus 1 into y1 plus 0 y2 plus 0 y3, that equals to 0. And in second equation 1 into y1 plus minus 1 into y2 plus 0 into y3, that equals to 0. So from this equation you get y1 is 0, and from this equation if y1 is 0, so you get y2 is 0. Okay, so if you combining these two, so you get here y1 is 0, y2 is 0, and y3 be any number, because you are not able to find the value of r3. This means y3 any value of alpha which belongs to a real one, because this is r3, so this is any real number. Okay, so because y3 be any real number r. Okay, so now this equals to here, so you find this value, and here you are able to find the y1, y2, y3. So this is collection of all y, and y is the vector. That first component is 0, second is 0, and third one any vector real value. So this means this transpose y says that alpha is any real r. Okay, so this means basically if we try to see that here, this is your x1 axis. Okay, this is your x2 axis, and this is x3 axis. Okay, or we take this is R3. Okay, so this is suppose your R3. Okay, so your Y is a X is zero component. Okay, Y is zero component, and this component Y3 component is any real R. Okay, so this means your any real R. This means this is uh, simply the X3 axis. Okay, so tangent space of that is X3 axis in R3. Okay, so this is your value of this tangent space. Okay, so if this is your frequency constant, and you are try to find the tangent space of that visible region, so that is the simple x3 axis in R3. So here in this example, the tangent space Tx at any point of x belongs to S is the surface, okay, which is defined by this thing, is a one-dimensional subspace of R3. Okay, so here you can write here in this example, the tangent space that is Tx at any point x which belongs to the surface S is basically one-dimensional subspace of R3. Okay, so this is the final result. Okay. So now the next topic is belongs to the Lagrange's theorem, and that Lagrange's theorem is basically depends on the uh, simple concept, that is the vector gradient of h and the gradient of your objective function both are parallel to each other. So this is a simple concept, and uh, Lagrange's theorem is basically based on that simple concept. Okay, so here we start the Lagrange's theorem for a simple case for two dimension, and then we generalize that Lagrange's theorem to for general n dimension. Okay, and then we will try to solve problem which is based on that Lagrange's theorem. Okay, so here in next page we next page. Okay, so here if we consider, suppose we consider functions of two variables, functions of two variables, and uh, suppose only one equality constants, only one equality constant. Okay, so this means is only one equality constant function, and this is from two dimensions, so this is from R2 to R. Okay, the constant function, the constant function. Okay. Here we call here we recall that at each point x of the domain, the vector gradient vector means gradient of hx. Okay. So to know that this gradient, if hx be any surface, then gradient is normal to that surface hx. Okay. So this gradient vector hx is basically orthogonal to the level set that passes through that point. Okay. So if we have taking suppose this is your point, any point that is a x star be a point, and suppose these are your level sets. Okay, so now if we take, there are some level sets here. Okay, and this point is your x star, and if we take a curve like that, okay, and here if we have this curve is suppose x of a and x of b, okay, and if we try to parameterize that curve, so now we choose here, we choose that any x star, and this is x with the two-dimensional, so this component are x1 star and x2 star. Okay, so this is the your vector x star. Okay, so this is the vector x star. So this is two-dimensional, so that's why that's component are x1 and x2. So this point says that your h of x star, because this satisfies your inequality constraint. Okay, so this means h of that x star that equals to 0. Okay, and assume that your gradient of that h star is not a null vector. That's why this is not equals to 0. Okay, so this has non-zero vector. So that's why this is a gradient of that is not 0. This is this one is the important property, because if your vector is null, then nothing is to do here. Okay, that's why here your vector is orthogonal vector is your some non-zero vector. Okay, so the level set through the point x star is the set, and that set is collection of all x such that hx equals to 0. Okay, so this is a simple a feasible region, that is those x that satisfies this equality constant. Okay, so now we parameterize this level set in the neighborhood of x star by a curve say xt. Okay, so we parameterize that curve xt. This has component x1t and x2t, where we have taken this value of t is some interval a to b. Okay, so here we parameterize this curve that is t equals to a to b. So we parameterize in the neighborhood of that point x star by a curve that is xa and xb, and that curve is depending on the t when t lies between a to b. So this point is goes through like that, and this represents a curve that is xt. Okay, so now what is the value of x star? X star. So this x star is same as x at t at particular value of that, because t equals to a here, you find that point. T equals to b here, you find that point. At particular value of suppose x at t star, you find this x star. Okay, and here you know that if we take the derivative at that point in this curve, so this is a non-zero, because here if we find the derivative of that, you find the tangent here. Okay, this is simple curve. So this is non-zero. You can find this thing where t star is belongs to interval a and b. Okay, so here we have that for all t that in belongs to interval AB, our hx, that hx equals to 0. So that the hx equals to 0. So this means that hx equals to 0, and here we take this, uh, can we parameterize that by a curve xt. So you can write h at x, and x is parameterized by the curve xt. So you can write here that equals to 0 here. Okay, so hence for all t that belongs to this AP, you can find here what is the value of d by dt if we try to find derivative of that of h of xt here. Okay, and that h of xt is 0, so derivative of that equals to 0 here. Okay, and now if we taking the derivative of two side here, d of dt of this thing and d of dt of this thing. So here left hand side d of dt of that, and here if we differentiate this 0 with respect to t, that equals to 0. Okay, so now if we applying the chain rule, so applying the chain rule, so we get here d by dt of this thing. So we differentiate h with respect to, okay, the gradient of that. So this means this is gradient of h x t transpose, and then differentiating with xt with respect to t here. So this is x dot of t, that equals to 0. Okay, so therefore from this relation you can get here this gradient of, and this is true for all t which belongs to AB. Okay, and here your t star is also belongs to that. Okay, so this means this is also true for gradient of h x at t star transpose and x dot at t star that equals to 0. So this implies what is the value of xt star. So this is a gradient of h. What is the xt star is simply x star t, and what is the value of x dot t star. So x t star, that is your x star here. Okay, so this is you can write here this is x dot t star that equals to 0. Okay, so if this product of these two equals to 0, this means the gradient of hx star is basically orthogonal to this point x dot t star. This is x dot t star. Okay, so this is orthogonal to this thing. Okay, and now now suppose that suppose that this x star is a minimizer of your objective function, that is f is from R2 to R, the minimizer of that objective function on the set, on the set, and that set is this is collection of all x such that hx equals to 0, because here only one equality constant. So on this set, this is your minimizer. Okay. So suppose your problem is for minimize f naught x subject to the constant at x equals to 0. So this is your problem. Okay. So now you have to find that x star is your optimum solution. That means this is your minimizer of your objective function. Okay. So here, if we take the composite function, so here the composite function that is if we define say any phi of t that is given by this phi t, this function is basically because your objective function of x and you have parameterized that x with this parameter t, your objective function is now f naught, and that is not x, but this is function of xt. So this is a function of t, that's why we define that function by another function that is phi t. Okay, and this achieves a minimum at t equals to t star. Okay, because this value has minimum when this x star. Okay, when t equals to t star, you have to find that is your minimum value, that is your x star. Okay, so consequently, you know that the first order necessary conditions, because you know that for minimization, you know that for any function which is we are able to find the minimum, so we take the first dy by df that equals to 0, the first order derivative is 0, and then we try to second derivative and we take that value is positive or negative. Okay, in general sense. Okay, so the necessary condition is that the first order derivative is must be 0. Okay, so consequently the first order necessary condition, necessary condition for the unconstrained extremum problem implies that you know that the first order derivative is 0. This will d by dt of this phi of this t star, that is 0. Okay, so by applying chain rule, so this implies that your 0 equals to, okay, so this 0 equals to d by dt of this phi of t star, phi at t star, because this is your minimum. So this means what is the value of d by dt? Phi of t star, what is the definition of phi t? Phi t is x f naught x t star. So we can write here f naught of x at t star. Okay, so you know that this is the gradient of f naught at x t star transpose and x dot t star. Okay, so now you get this gradient of this f naught at this x of t star. X of t star means this is simply x star. You can write x star. Okay, transpose with x dot t star. This is x dot t star. So that equals to 0 here. So this is 0. Okay, so here you look here. This means you see here this gradient of f naught x is orthogonal to x dot t. Okay, so this implies this gradient of f at x f naught x x star Okay, this is orthogonal. This is orthogonal to this x dot t star. Okay, so in fact that this x dot t star is tangent to this curve. Okay, so basically this x dot t star, this x dot t star is, this is a tangent. This is your x dot t star. Okay, because this is your x star, so this is your tangent. Okay, and here see here, this is from here, this gradient of fx star is orthogonal to this vector, and here you take here this is also gradient of f x star. Okay, so this is also orthogonal to this x dot t star, and this is the tangent curve, and here from here this is also orthogonal to this thing. Okay, so either in this direction or in direction, this is also perpendicular to x dot t star tangent vector, and this is also perpendicular to this thing. Okay, so this means any vector that is suppose if this vector is, suppose this curve is here, and this point is your x, this is x dot t star. Okay, this is x dot t star, and here you see here, this vector is orthogonal to, and that vector is gradient of f naught x star. This is orthogonal to this thing. Okay, and also from here you can see that this is your, from first this is your x dot t star. Okay, and here this is orthogonal, this is gradient of hx star. Okay, so this is also orthogonal to this thing, this is orthogonal to this thing. Okay, so if this two vector x dot t star is same, this is same, and this vector is also orthogonal to this, and gradient of h is also orthogonal to this means these two are parallel. Okay, so this means these two are parallel vector. Okay, because both are perpendicular to same tangent vector. Okay, so here we can write all those things in next page, because here no space is left in this page. So we take the next page. The next page we write all these things. The next page, so we can write the fact that this x dot t star is tangent to the curve that is xt at x star. This means that gradient of f naught x star is orthogonal to the curve at this point, that is x star. Okay, so here this gradient of hx star is orthogonal to x dot t star. So therefore the vectors, that is gradient of fx star and gradient of this objective function, this star, are parallel. Okay, so these two are parallel, either in the same direction or in other direction. Okay, so that is, you write this gradient of this f naught as star. If two vectors are parallel, this means one can be expressed as a scalar multiple of second. Okay, so this means this gradient of this is a scalar multiple of this gradient of hx. Okay, so hx star. So this gradient of hx star. Okay, so this is basically final result. You know that your this gradient of hx and gradient of these two are parallel, and here this one can be written in the scalar multiple of second. Okay, so now by using this concept, your Lagrange's theorem, Lagrange's. Okay, so this is your Lagrange's theorem, and this theorem apply on the problem which has only equality constant, non-equality constant. Okay, तो ऐसी प्रॉब्लम जिसमें सिर्फ और सिर्फ इक्वालिटी कांस्टेंट है, उस प्रॉब्लम को हम सॉल्व करेंगे बाय यूजिंग Lagrange's theorem. Okay, so this theorem and this theorem is if we write down this for our n equals to 2 थे और p equals to हमारा that p is only one equality constant, that's why we find that result. Okay, so our Lagrange's theorem says that let the point be a minimizer. This is a problem of minimization. So this is problem of the minimizer of objective function, and that objective function is R2 to R subject to the constraints subject to the constraints, and constraints are equals to 0, and because here p equals to 1, here p equals to 1, that's why here we take only one equality constant. So here h is mapping from R2 to R. This is a statement of Lagrange's theorem. Okay, so then this gradient of objective function at this minimum point and the gradient of hx star, this are parallel. This are parallel. Okay. So this means parallel in the sense that is, if your gradient of hx is non-zero vector, because this is not null vector, then so this condition is important because this is null vector नहीं होना चाहिए. Okay, the gradient of that is non-zero. Then there exists a scalar. Okay, and that scalar is, we take that lambda star, because this is problem of minimizer optimum solution, so we can write here lambda star. This says that this gradient of f naught at x star plus the lambda star, this gradient of fx star, that equals to 0. Okay, and here this lambda star is Lagrange's multiplier. So here lambda star is Lagrange's, okay, Lagrange's here, not n, Lagrange's, Lagrange's, okay, Lagrange's multipliers. Okay, so this is a Lagrange's multiplier, and note that this theorem is also hold for maximizer. Okay, so note that the theorem is also valid. Theorem also holds for maximizer. Okay, because in minimization problem or maximization problem, your first order necessary condition, that is d by that equals to 0 always. Okay, so here you have to, this problem is also holds for minimization problem and also for maximization problem. Okay, so here don't confuse me about that this problem is minimization. Okay, so this problem is minimization or maximization, this theorem holds for both cases. Okay, so we now generalize that Lagrange's theorem for the case. So if we generalize that generalization, okay, so generalization आप कर सकते हो by using your objective function. If we taking from Rn, not R2, this is R2 this, and our this H is from, there are not only one equality constant. If suppose this is p number of inequality constants. Okay, so now here p is less or equals to n. So the Lagrange's theorem, in that sense, the Lagrange's theorem becomes like that. So let x star be a local minimizer or maximizer, anyone, okay, of objective function, and that objective function from Rn to R. So we generalize this same concept. Okay, gen R2 to R, subject to the constants that Hx is 0, and here this H is not a single one, but this H has H1, H2 up to HP, so that's why this has P component. So this is mapping from Rn to Rp, and here P is less or equals to N. Okay, and if we assume that, if we assume that your x star, that x star is a regular point, this is a regular point, then there exists, a lambda star. Here only this is a scalar one lambda, but here if this lambda is for this equality constant, if there are p number equality constants, so this lambda star belongs to lambda 1, lambda 2 to lambda p. So here this lambda star belongs to this rp. Okay, so there are lambda 1, lambda 2 to lambda p, such that the derivative of objective function at this optimal point plus lambda star transpose multiplied by derivative of h x this equals to 0 transpose. This is a generalized version of this theorem. Okay, so this is only the gradient, but here we use the derivative because our components are okay. So there are more components. So that's the derivative means gradient of that, gradient of f1, h1, h2, and so on. Okay, so that's why we write here this thing. So this is the final Lagrange's theorem, and that in this theorem, there's your inductive function is from Rn to R, and your H1, H2 to Hp are equality constants. Okay, so here, okay, so now if we take an example and we see that, okay, if there is a problem and okay, okay, next page, next page, although one day क्लास है तो एक बचे हैं ठीक थोड़ा और करा देते हैं नेक्स्ट पेज take example if we consider the following problem. Okay, this problem is minimize objective function, minimize f naught x subject to constants where hx is 0. Okay, so this is simple problem. Okay, and what is your objective function is what is f naught x? F naught x is here. Suppose we take simple function x, and what is hx? So hx is if we take that hx equals to suppose x square if your x is less than 0, and this equals to 0 if your x is lies between this thing, and hx is x minus 1 whole square if this x is greater than 1. Okay, so here if this type of wave problem is defined, and here what is the feasible set? Okay, so what is the feasible set? So here we take here hx equals to when x is less than 0, so this equals to x square. Okay, so and when x is greater than 1, this equals to x minus 1 whole square, and when this 0 and 1, this hx equals to 0. The way we have to subject to condition is hx equals to 0. So when hx equals to 0, when hx equals to 0, when we take this interval. Okay, so this is your feasible set. So the feasible set is evidently that is closed interval 0 1 because here hx is 0. Okay, so if this is your interval, so you have to clearly what is the minimum value because your problem is minimization and your x is varies from this. So this is your feasible set 0 and 1. So if we take x values and which value is minimum one, when we take x equals to 0, this objective function has 0 value. If we take x equals to half, that objective value is half. If x equals to 1, then f not equals to 1. So which one is minimum? 0. When we equals to 0, when we putting x equals to 0 here. So clearly your x star equals to 0, your functional value is 0 here. So this is a local minimizer. Okay, but however, if we try to find what is the value of this f naught derivative of that f naught this, okay, prime of that, so this becomes 1 if we differentiate this, okay, with respect to x, this becomes 1. And what is the value of uh, this value at pose x, or we take any value of x star, okay, because x star like this thing. Okay, so here similarly if we take what is the value of hx is 0, so what is the derivative of that? So x prime at x star, that is equals to 0 here. Okay, so therefore So x star does not satisfy, does not satisfy the necessary condition in Lagrange's theorem.
Hello, sir.
Hmm?
If not, does x equal to 1 and क्या लिखूं?
And h dash x star that equals to 0. This h dash, because here this hx equals to 0, this is your problem. So if we differentiate this at x star, that is also equals to 0. Okay, and your Lagrange problem, Lagrange theorem says that the gradient of f naught at x star plus lambda star, and that is the gradient of hx star, that equals to 0. Okay, so here if the gradient of that, this means this derivative of that this equals to 1 here, and this plus of lambda, this is scalar 1, and here this term is 0, this term is 0, that equals to 0. So here 1 equals to 0. So this is not possible. Okay, so that's why we write here this not satisfies the necessary condition in Lagrange's theorem. Okay, this is not satisfied, this theorem. Okay, so because why this is not satisfy this thing? Because you remember that your Lagrange's theorem, you know that your gradient of that is not a null vector here. Okay, and here this is null vector. That's why so this condition is not satisfied. So if you look in Lagrange's theorem, you clearly mentioned that your gradient of hx star is never null vector. Okay, so we can write here. Note that why this is not satisfied here. So note, however, that this x star is basically not a regular point. Okay. So first of all, you have to check your point is regular or not. Okay, and then you satisfy this Lagrange's condition. If your point is not regular point, then this theorem doesn't satisfy. Okay, so this is not a regular point, which means, or which is why Lagrange's theorem does not apply here. Okay, does not apply here. ओके, तो ठीक है, तो आज के लिए इतना ही करते हैं, काफी देर हो गई। फिर लैग्रेंज थ्योरम पर हम न्यूमेरिकल जो है नेक्स्ट टर्न पे हम कराएंगे। और ज़्यादा हो जाएगा तो फिर आपको फिर समझने में मुश्किल होगी। तो नेक्स्ट टर्न पे हम एक लैग्रेंज प्रॉब्लम हम लेंगे और उसको ट्राई टू सॉल्व द एक्सट्रीम पॉइंट्स, उसके हम फाइंड करेंगे। तो ठीक है, तो आज इतना ही करते हैं। ओके,
Thank you, sir.
ओके सर।
Thank you, sir. You, sir.